Okay, welcome to the next talk in the One World Minds seminar. Our speaker today is Dr. Richard Tsai, who's a professor at UT Austin in the mathematics department and also the Odin Institute, and he'll tell us about data-induced multiscale losses and efficient multivariate gradient descent. So, Richard, thank you so much for being here, and please take it away.
Okay, well, thanks for the invitation. Well, I'm glad to be here, and I will try to talk about a few things that we've been looking at in this direction. And this is a joint work with Tsai He, who is currently at CALS, Louis Liu, who's a graduate student in the math department at UT, and me. And this research has been funded by National Science Foundation as well as the Army Research Office. Okay, so I'm gonna just assume, I'm gonna start with some kind of general description of, not assuming that everybody is an expert. So in many situations, we're interested in data because we're interested in learning from data. And very often, data are embedded in higher dimensional spaces. And so here, on this slide, you see a very common data set that people use to analyze or use to develop their models. It's a collection of handwritten digits, right? And digit pixel image, essentially black and white, but it's grayscale. So the intensity. So here you see that there's an image that looks like a 1, and it is actually, you can regard it as a matrix, 28 by 28 matrix, and then each entry in the matrix carries a number ranging from 0 to 1, and in this case 1 means it's very dark, it's black, and then 0 means it's white. And you have grayscale, right? So as you vary the intensity from 0 to 1. So we can, instead of looking at it as an image, we can treat this image as a point in R784, where 784 is actually 28 squared, right? So this is actually a point. This image is a point in R784 dimension. So it's a relatively high dimension than the usual things that we're dealing with, like in R2, R3, R4, etc. So let's say if I recall correctly, in this MNIST data set, there are approximately 60,000 points, 60,000 images. So which means that you have a distribution of 60,000 points in this very high dimensional Euclidean space. And you can ask, so how are they distributed? And if you use such kind of set of data points to learn a classifier, to learn how to identify different alphabets or different digits, then what are the consequences? How does your classifier depend on the geometry of your data distribution? So this is, in a sense, this is a question that we started to ask during the pandemics. My motivation at that time is to say, okay, I would like to do something completely different from what I used to do, which is solving PDEs. So let's look at data and see what we can say about it. So there's a related thing which is called manifold hypothesis, and it kind of states that if you look at distributions of say natural images or the common images that you may encounter, then and embedded in such a way, then their distribution roughly concentrate on lower dimensional manifolds, a submanifold that's embedded in this high dimension space. And suppose this data, so let's say we call such kind of manifold data manifold, and you on this data manifold you have a probability distribution, and then you can model the discrete data as being some kind of IID random variables from this distribution. So what would be the consequence of such kind of feature or fact, right? So in this case, we start to ask, so what happens if I have a higher resolution camera and that digitize handwritten into 280 by 280 image, which by nowadays is still a very small image, right? But the embedding space would be much higher, much higher. But if you still digitize this 60,000 different handwritings, they should roughly, look the same. So what I'm trying to say is, you know, the red line on the bottom of this slice, right? So it seems that at least the way I set it up, the embedding can be arbitrary. I can do 784, I can do 10,000, etc., from the same set of data points. So there's some kind of arbitrariness in this. And what would be the consequence of this arbitrary embedding? So that's what, and how would that influence, let's say, our learning or the stability of our, let's say we use neural network, the stability of neural network, like that. So this is the starting point of our quest. You know, so as a mathematician, we say, okay, let's look at much simpler questions. Hopefully, you know, from a toy problem, we can kind of extract some insights that's relevant to the question that we started asking in the previous slides. So let's be concrete in this case, but also be simple. So let's assume that, okay, we have a data set that consists of finite number of points, n number of points, and it's labeled data sets, right? So for each x, which is, you know, the coordinates, and you have a label. So in the previous example, then you have an image, and this image, the label of this image will be whether it's 1 or 2 or 10 or 9, etc. Okay, so in this talk, we worry less about G, but we worry about the distribution of Xi, okay, and their influences. Now, and just to add a little bit of kind of elaborations. So let's say that you know, up to a kind of a unitary transform, right? You know, the distribution of data is quite simple, right? So if you undo the transformation, then you know, the data actually lies when there's no noise in the coordinates in xi, then let's say that the data lies on so in this case on the x-axis over here. So these blue dots denotes the data points. And you can also consider a situation where actually there's a little noise in the y coordinates. So then, you know, each data point will be polluted and it will be perturbed into the set of red nodes that you see over here. You know, they spill over into this the y direction like that. Okay, then so in this case, then our model, so what we call the data manifold would be, you know, the x-axis. And then we have a distribution defined on this on the x-axis. And then we can also consider a distribution that's roughly concentrating on the x-axis, roughly concentrating, meaning that you know there's a small variance for the noise in the y directions like that. Okay, so this is the simple first model. And then after making some assumptions, because we assuming that you cannot further reduce the dimensionality of your coordinates anymore. And this is related to these two assumptions. And then to make things simpler, then the noise in the normal direction of your data manifold will be just some Gaussian noise like that. And we're going to use this notation to denote the empirical means with endpoints. And then, of course, we say that you know we know that when n goes to infinity, then by the law of large number, then it will converge. The empirical mean will converge to some expectation with respect to the distribution, your data distribution like that. Okay, so then we study the simplest question that we can ask. So what happened to linear regression? So what happened if we try to fit you know, a linear function to our data? Right, so the linear function will be defined by two parameters, w and wx and wy. These two are the weights that we try to find, and we're going to try to find the weights by you know, so this will be the function, right, our model, and we're going to minimize you know, how it fits the label g, which is assumed to be you know, a real number, right? And then, you know, least square setup, so formulated this way. And suppose you can find the minimum, so you can find the parameters wx, the optimal parameters wx and wy. Then we're going to denote these optimal parameters using superscript star over here. Then you have your function that you would try to use for inferences. Now, the interesting thing is in particular is that what we ask question, so what is the normal derivative of your learning function with, so in this particular case, what's the partial derivative of your learning function with respect to y? So in this simple function, then of course it's related to the wy parameters, this parameter wy star. Right, so why do we ask this question? So suppose we solve this problem and then we want to use it for inference. And somebody, even in the beginning when sigma equals to 0, so all your data points lie on the x-axis. But when after training, your friend asks you to run the inference, but with a small contamination in the y direction. So the y coordinate is non-zero anymore. And then you would like to know how stable is your learning function, right? So then a simple question to answer would be to find out what's the normal derivative of your learning function in the direction normal to your data manifold. Right, so then you see that for any positive sigma here, there's actually a unique solution. Wy star is uniquely determined. But when sigma equals to 0, then you see that you cannot formally solve this problem because there are more than one solution to any wy will work because it's always multiplied by 0. So your data, so we like to say that your data doesn't let you see how you should get your parameter y, right? So we also say that so in this case, then wy is not a trainable parameter. So when sigma equals to 0, this linear regression problem is ill-posed in the sense that wy there's no unique solution for wy. However, you can still do, if you stick with this kind of, deep learning strategy, let's do gradient descent to try to find a minimizer. Well, so then it depends on your initialization because wy in the course of gradient descent is never going to change. So it will stay the same as how you randomly initialize these parameters, while w it will converge to an optimal parameters. Then we can go a little bit further, right? So we can try to estimate these parameters. So when in the context when the number of data points is big. So after quick calculations, you can see that the optimal parameter wx star looks like this, and this is how it should be. The first term is how it should be if you set up the least square problem in 1D. This is how it should be. And then it's perturbed by this guy. And wy over here, when sigma is not 0, then wy has this term over here. Has this can be written in this expression over here. And what I want to emphasize is this term colored in blue, which appear to be very interesting to me. Why is that interesting? It is interesting because let's say that we assume that the noise sigma is very small. So sigma is a small number. And if you have a fixed number of data points, then this roughly, assuming that this is order 1, then this number here roughly controls the size of your wy star, the magnitude of your wy star. And for fixed sigma, if you're allowed to generate or draw more samples, enlarge your n, then you see that as n goes to infinity, then your optimal parameter will be converging to 0, which is a nice property because then it says that imagine here you replace this quantity here by 0. It means that your learning function is going to remain constant in the direction normal to your data manifold, which is very stable, right? So this is kind of interesting because it tells you that by enlarging your data set, you can in this particular context you can control the stability of your learning function when you are making inferences of data points that's say close to the boundary of your data distribution. Okay. So what are the consequences to inference stabilities? So we kind of, first of all, we kind of assume that, as I alluded earlier, that data are are distributed on a submanifold, and this makes sense in a lot of applications. For example, in certain dynamical systems learning, where your dynamical system has certain invariances, the data sets will be just gotten from let's say from a set that satisfy those invariances, and so when this is the case, when data concentrates on submanifolds, then there might be a set of parameters in your neural network that's not trainable, similar to the simple linear regression problem that we have seen in the previous slides, right? This WY in the earlier case are not trainable because your data doesn't vary in those directions. So then you can see that if your data really concentrate on the submanifolds and it doesn't vary, data points don't vary in the normal the manifold's normal direction, then the parameters related to those directions are not going to be trained through your optimization algorithm. And then we also see that so there's because of these parameters are not trainable, then they are initialized randomly. So this randomness kind of persists. As you feed forward your network, the randomness will persist and then will influence your output, the output of your network. We have worked. So in particular in this the second paper on the lower right here, so we have work that tells you, suppose your manifold curves just a little bit. So the curvature of this manifold is another small parameter. Then this curvature will have significant influence to your learning as well, to the stability of your learning function as well. Right. So this is the first case when data just concentrates strictly on the submanifold. If now you allow your data to spill over a little bit into the normal directions, in the previous case, it corresponds to sigma being non-zero, then we see that, what we have concluded in the previous slides, will also be true in favorable conditions. It means that the network's output stability can be controlled by sufficiently large number of data points. And the number of data points has somehow scaled with, say, the variance of your noise in the normal directions. Okay, so I like to see whether these, these statements actually make sense on some common data sets, just to have a sanity check. So here we're doing a simple experiment. We're going to model, let's say, we're going to model the MNIST data set, all 10 digits, as pretending that they are lying on a on an affine space spanned by R783, and keep one direction to be the normal direction of the data manifold. So which means that we can use SVD, or use principal component analysis, PCA, which is based on SVD, to find such kind of directions. So the last principal directions will be corresponding to a normal the normal direction of our data manifold, and we assume that the data will then distribute roughly on the remaining 784 directions. And let's say we pick a image, so which would label 9. So this is the image. And then we're going to consider perturbing this image in two particular way. One is in the normal direction. I'm just going to add noise vectors to this image, of different magnitude. And then this is what you see from in the sequence of images appearing on the top of your screen. So what you see, to me, it's very interesting. So you always see this 9 very clearly. It doesn't, the noise doesn't destroy the structure of 9, but the contrast of the image is decreasing. Okay, but let's consider adding noise in another particular direction. In this direction, this denoted by the pink arrow, this is a particular direction that's tangent to your data manifold. But it's particular because it's in the direction where your loss function with the gradient of the loss function with respect to the input x. So that in that particular direction. If I keep adding that, then very quickly you see that well, the structure of 9 is going to be perturbed, and in this case, it seems that we have an invasion of the 0 digits coming in, and then eventually you get to another digits like that. So it seems that by this experiment, it seems that there is something to this kind of manifold hypothesis, right? The geometry in this case, even though it's simple, the geometry actually has some kind of different give you different properties.
I think we may have a question, Richard. Can Rohit?
Yeah. So the PCA that you take is of the entire data set or just the examples of
the entire
9?
data set? The entire data set. So even with a PCA applied to the entire data set, this is still true. It's kind of interesting. That's people asked me this question before, and we were surprised. Yeah. Anyway. Okay. So then let's try to do some more experiments. Okay. So as I mentioned before in this in the 2 or 3 slides ago, there's a set of parameters that's not trainable. So in the case of deep neural network, this set of parameters will be a subset or a subspace related to the weight matrix connecting the input layer to the first hidden layer. Now we can prove that in this particular setup, there will be something that's not trainable. So this time we're going to add 2 types of noise. One to the network's weight. We're going to do surgeries, or we're going to change network's weight. So this is related to W1 plus this particular noise. The magnitude of the noise is denoted by eta, and then it's a particular low rank matrix is being added, and this low rank matrix is basically in the normal direction of the manifold. And when they change it in the plots on the right, they will be corresponding to the vertical axis. And then the second type of noise is what we studied in the previous slides. We add perturbations to our image, right? And then we perturb the image in the normal directions, right? So remember in the previous case, the structure of 9 seems to remain coherent, when we add noise in that direction. So this will correspond to the level of noise in this particular setup will correspond to the horizontal axis like that. And this time we pick number 2. So according to our theory, this set of weights, the noise added to the to your neural network is not going to influence your output if you don't perturb it. So when you give the original image on the data precisely on the data manifold, then you see that in this case, no matter how much you add, right, in this range here, you can perturb your network, the input weights a lot, and it wouldn't change the output of the network at all. So this is the output before you do this softmax and then you map them into digits. So after you do softmax and map it into digits, you will see that, well, you have this region where your image as well as your image being polluted and your network being polluted in a particular way, and it will stay with the same classification. It will be a number 2. Now, if I add noise to the normal direction, then this normal direction will start to interact with this component of the weight in your network. And then this is what you see. So you see that you can go. So in this particular case, if I pick this level of here, it goes from 2 to 1 to many different colors, and then to it seems that in the end 7 dominates like that. So these 2 are experiments somehow kind of illustrating the results that I mentioned a few slides ago. Now we can do a more formal analysis. So assuming that we have a standard feed-forward deep neural network and activated by ReLU, then we can write our network recursively in the following form, right? So this is the previous layer being activated by ReLU, and then you form a new affine functions like that, and this goes on, right? In a similar fashion. We single out the second layer or the first hidden layer because we want to show the influence of this particular part, this component over here, and how it goes through the network when you feed forward. And we're going to measure, because this is the part. So let me take a step back. I got a little bit too excited. First, the notation. So assuming that we're going to train this network on these, in following the previous example on the MNIST data set. After training, since I already have the superscript over here, so wherever you see an overline over here, these are the optimal weights that's found by your favorite optimization, gradient-based optimization algorithm. And as we mentioned earlier, there's a component, right? There's a set of weights that's not trainable, and in the first layer, and that is denoted here by W1Y. And Y here, because we kind of rotate, so Y is always the direction normal to our data manifold. So this Y here will be, whether you have noise in the normal direction or not. So when you have non-zero Y and it interacts with this matrix, which is not trainable, then we would like to see how this will come out at the end, at the output of the network. So we can do this recursively by looking at the difference between at each layer L. When you have a clean data point without any perturbation in the coordinates in the manifolds normal direction, and with some perturbation that's the amount of Y like that. So we would like to get an estimate of this difference, and this difference here, because of this recursive structure of your neural network, you can have a very fast inequality. You can come up with an inequality like this. And then you can just, in a sense, stack them up and follow through to the last layer. And then, and then we're able to have the following proof, where the change, this particular change in the final output, the L2 norm square of this is going to be bounded above by the expressions on the right-hand side. These are the first factor here on the right-hand side are the product of the matrix norms of all the trainable weights, right? Those are just determined by the data and by how you optimize, and they're optimized in some sense. And then the sum here, and then you see the colored portions in the terms. Those are the, how the randomness in your initialized weights, and then also the noise in the data manifold's normal direction will come into play, will influence your network's output. There's a quadratic term, but not surprising. I mean, in a sense, we were squaring over here, and then this is a third order term like that. Okay. The second thing that is kind of interesting is that there's a gradient of Hij here. And then this H is essentially, the output of your first hidden layer. And then you're looking at the spatial gradient, right? So how it depends on your input, the change in your input. So that also come into play, and that seems to be interesting to us. Okay, so then as a numerical analyst, right, you have this estimate, then we would like to see whether we can verify this estimate through some numerical experiments. So here's a very quick thing. So we can say one thing we realize is that suppose you have a clean data set where all the x's lie on a submanifold, and then you see that there's non-trainable. So then there's this random effect over here, and you don't like it. And how do you kill it? Based on our experience or on our toy problems, why don't we just add noise to the normal to our data points, so that it spill over to the normal directions? And then we also learn from our least square problem that after we add noise, suppose we can generate enough training data set, sufficient number of training data points, then we can control the stability of basically the size of this guy, W1Y. So why don't we try to make some study of that? Right? We can, or you can also say that let's try to do a more conventional approach by adding some regularization to your loss function to your training model. Suppose you don't want to do that, then we can experience based on our experience in the based on our experience in this linear problem, we can say we can add noise to the data, but then at the same time we better make sure that we increase the number of samples. And then see what's happening. And then the two plots kind of corroborate with what we've been saying. So for example, on this plot on the lower left corner, so we set up we try to learn a function, with some simple functions in some high dimension, and the horizontal axis tells you how much the amount of noise that we add to the normal directions, the sigma. And it's a log plot, base 10 plot, I think. And you see 3 curves. So these are corresponding to the number of hidden layers in your neural network, fully trained. And so the first message is that as the noise level, so we fix the number of data points, right? Then we see that as the noise level increases, then the error decreases, which is good. But then you also see that there seems to be a separation between the red line and then the blue and the green line. And what does the red line correspond to? It corresponds to a single network with single hidden layer. And then the other two are so-called deep neural network. Now that's switch a situation. That's fix sigma, fix the noise level, and that's try to enlarge the data set. And then here you also see that the error decreases. As remember our this estimate, very quick estimate from our study of linear regression. There's this 1 over sigma times square root of n, right? So fix sigma, then n increases, then wy would decrease to 0 in that particular way, and this is a profession of that. So again, you see that what I want to point out is that there's a fundamental difference between a shallow network and deeper network. There doesn't seem to be too much difference between a 4-layer and 6-layer network in this particular study like that. And as we know, there are many fundamental differences between shallow and deep neural network. Now, we can understand the effect of adding noise in a more systematic way, and try to interpret as doing a particular way of regularizing your original loss function without changing formally the form of the loss function, in the following way. Suppose I know the manifold, the normal direction of the data manifolds at every data point. X is my data point, right? The coordinates of the data points. And I'm going to add epsilon amount of noise, sufficiently small. So small that, it's actually within the reach of this supposedly smooth manifold. So this is my noise model. So then instead of so after adding the noise, the original empirical loss becomes this form, becomes L tilde n, where you evaluate your network at this perturbed x coordinates like that. The label is unchanged. Okay, so what can we say about this? Well, the first thing we say is that suppose we really do this, and if I denote by P sub m to be the projection of this data point x tilde back to the manifold, some kind of L2 projection or closest point projection back to the manifold, then so in this, then you see that suppose I have a clean coordinates xj, evaluate the label at this particular clean coordinate, it's called g sub j, and so this evaluation will be the same as if I'm evaluating the same function g on any of these data points, perturbed data points x tilde projected, right? So but our view, you can change your interpretation of this expression. You can say that, well, in this case, if I look at the composition of this projection together with G, I'm defining an extension of my label function into the normal space, into the entire ambient space, right? And this will be, if this is the closest point projection, then this function G star will remain constant in the normal direction of your data manifold, right? So this is the first observation. Now the second, now then we just replace G sub xj or replace gj by G bar in L tilde n. So then effectively what we're having is this. And what that means is that I'm going to change a viewpoint, right? I'm going to assume that x tilde I are my data point, unperturbed ones. And what I'm training for is actually a label function which is constant in the normal direction. Okay, so then of course you can come up with this kind of diagram, but this is actually what it means. So in the end, you're really by adding this noise in this particular way, you're training for a function, a label function, to approximate a label function which is constant in the normal direction, which in our sense is very stable, because if you have noise in the normal direction, it's your prediction is not going to change. Okay. All right. Of course, you can say that in practice it's hard, unless you're a super expert on manifold learning, etc. Maybe it's hard to estimate the data manifolds normal directions. So then you can take a step back and say, okay, I'm just going to add uniform noise to all the coordinates, but small. And then from this diagram, you see that, okay, you perturb your original data points. There's a tangential perturbation. This will cost you some accuracy. And then you have the normal directions like that, right? So then you can do your estimate through some kind of triangle inequality, etc. And then also from our experience in solving linear regression problem, we know that, okay, so because of this, we better make sure that we can have enough, we will have enough data points in order to fully benefit from the effect of adding noise. Okay, so then we do another study, right? So in deep neural network. So earlier, we can prove that if you have linear networks, okay, the simplest case of linear network is when is linear regression. Then the way your learned function is changing with the perturbation in the normal direction, y direction, is big O of 1 over sigma squared times n beta. When for linear network, beta equals 1. Earlier we see what I wrote, I put on the screen is 1 over sigma times square root of n. It's the same thing. But what happens if you have a ReLU activated deeper network? So we have no proof so far. A lot of intuition, but no proof. And it seems that the beta is at best 1/2. And this is from empirical observation, which I try to illustrate here with the table on the bottom. So the first row of this table is the dimension of the related to the normals. How many normals you have? Independent normals you have? 10. And then this is network with 1 hidden layer, 4 and 6 hidden layer. And then we try to estimate beta from numerical simulations. So these are the estimated beta. So you see that with shallow network, these set of experiments suggested that you need, the scaling you need of n is worse, right? You need more. Whereas, the deeper you go, it seems that, you're bordering, you're kind of bordering beta equals 1/2 like that. And again, there seems to be a gap between, shallow network and deeper neural networks like that. Okay. So that's understanding after training, what would be, the worst possible outcome like that. So now in the remaining, say, 10 minutes or so, I will quickly go through what are the consequences in training. And this is our effort and what we found so far. So let's say that we're going to say that the data distribution, earlier we say that this manifold hypothesis, the data are distributed on some kind of lower dimensional manifolds in a high dimensional embedding space. And then we're gonna in a sense generalize this. We're gonna say that this data distribution is multiscale. In the way that's most consistent with what we're talking about is that in this MNIST data set, we assume data set, the data points are spreading over some kind of lower dimensional manifold, and then it has a small perturbation or small variance in the normal directions. So that smallness in the variance in the normal direction is, and versus the variance in the tangential direction is what we call multiscale. We assume that there are some gaps over there. And let's see whether this kind of a multiscale assumption, we can observe this kind of multiscale assumptions in some more realistic data. So this is a credit card data set. They're cleaned up, and then they are doing k-means, so you know which group. So their different groups are colored, differently. So then if you project just onto, and then we use principal component analysis on just use the simplest one. We use principal component analysis on this data set. We project the data set onto the plane or the two-dimensional subspace spanned by the first two principal directions. Then you see something like this. So this is a distribution of a cluster, and so the span of the red arrows and then the black arrow is what we mean by this distribution being multiscale. And it's a data set that lives in much higher dimension. But even when you project all the rest of the dimension out onto the first two dimensions, you see that they're still very concentrated. It's very structured. And then this is the third versus the second. You also see this kind of structure. So this kind of give us some kind of convincing that maybe this direction is meaningful to look into. Okay. So the next thing that we do is so this is another example, right? So we look at the principal. So we go back to the MNIST data set. And then we just use PCA and we look at the distribution of or the magnitude of the singular values found, which corresponds to the variances in each of the singular directions. And you see that how fast it decays. So this is the dimensions, right? So we are up to 784 dimensions. So you see the singular values or the variances just decays quickly. So it just the data is somehow very concentrated. And then when you project it down to the first principal axis, you also see some kind of structures, for example, over here. Okay, so how does multiscale data, so let's acknowledge that. So and then we can ask, how does multiscale data set affect training? So the first thing that we find is that, well, the data set can determine the behavior of the loss function. And we're highly motivated by the following two works. So the first work is work by Kohn and Tao, where they consider two-layer network, and then the activation is periodic. And then in this case, they assume that the label function is multiscale. So there's a multiscale expansion of the label function. When you put it in, then your loss function is multiscale because it has epsilon popping out of your loss function. And then, of course, you will have, when you look at the gradient of the loss function, you will also have different orders of epsilon coming out. What they prove, a very interesting result is that, so in this kind of, following this kind of hypotheses, if you employ a deterministic full gradient descent to the loss function, the resulting loss function, the dynamics of this gradient descent algorithm with a fixed learning rate could exhibit stochasticity. So that's very interesting. And then the second paper is a paper by Ma and collaborators, and they studied, shallow network activated by ReLU. And in this case, it's closer to what we're gonna analyze, or what we analyzed, a multi-scale data where the coordinates of the data points xi, after suitable, let's say, unitary transformation, can be arranged into coordinates of different magnitudes. Say x1 will be one type of magnitude and x2 will be, let's say, smaller magnitudes like that. So after suitable rotations and translation, then certain coordinates is larger than the other one. But yeah, so that will be related to the variance in those coordinates like that. Then of course, then the resulting loss function, they say that it becomes multi-scale, and then they stated that it will affect the stability of your gradient descent algorithm. And we're going to find out exactly how. So I am going to, because of time, let's see. Okay, so I can, yeah, I think this is this has contains a message that I want to deliver anyway. So to start with, let's consider linear network. So all the activation is just identity. So in the end, you are optimizing for all the intermediate matrices, which multiply to a simple vector like this. But you do your gradient descent anyway. So this the three authors, they derive in this nice paper, they derive that if your weight function, if your matrices are initialized in a certain way, then the gradient flow, so the gradient flow with respect to all the weight matrices can be summarized into a dynamical system governing how the so-called end-to-end weight would change. It's a ODE, and it goes like this. And suppose you assume now that in this particular setup that we have this, the distribution of x is a multi-scale. So in this particular case, we go back to our scenario where, your data points concentrates mostly on the x-axis with a small variance in the y direction. So then this is the phase plot of that ODE in the previous page. Oops. This is the phase plot of this ODE, phase diagram. The white star over here is the theoretical unique minimum. Okay. And of course, this is x direction and the vertical axis is the y direction. So suppose you start out from somewhere over here and initial weight. So this is, sorry, I take it back. So this is Wx, right? So this W contains two components, Wx and Wy. So this is Wx and this is Wy. Suppose you start out with an initial condition that's over here. You're going to follow this flow. You're going to be attracted to a slow manifold. And this slow manifold is going to pass through this theoretical unique solution. And once you get to the neighborhood, you're going to travel very, very, very slowly for a very long time until you arrive at a suitable neighborhood of this white star. If you start out, unfortunately, over here, then you're going to be attracted to the origin, and then you will never escape. like that. So the multiscaleness in our setup, where the data concentrates roughly on the x-axis, will come out to be related to the existence of this slow manifold, and then the difference in the magnitude of the vector fields that you see over here. You will be possibly quickly attracted to the slow manifold, but then you will spend a long time going, virtually tangential to the slow manifold, and almost never get there unless you wait. And what you see is what I just said is, can be observed from this plot on the lower left corner. We do a full gradient descent. So the blue line is the history of gradient descent of the weight in x for the x coordinates. Very quickly, you get to the right location and it doesn't change. And then you look at, if you just monitor the training loss and you believe that you can determine when would be a suitable time to stop your training by following your training loss, then you see that very quickly your training loss also plateaued. But that's not, because the training loss only measures how you fit data within the distribution. So when you look at, in this case, we know the ideal value of WY star. If you look at the distance between where you are and to the ideal location, then you see that you actually would, you're not there yet. You're very far from being zero. So, and then we say that we know that the magnitude of WY star, or whatever you get there, will influence how your network function performs when you try to, in the normal directions. So this just shows you that when your data distribution is multiscale, then just monitoring the training loss might not be sufficient to guarantee some kind of stability in your network's output, like that. Okay, so then we can further generalize these things to fully nonlinear network, ReLU, activated by actually a class of, we're able to prove for a class of activation functions. Suppose, again, after suitable rotation translation, your coordinates have this kind of, can have this kind of expressions like that when epsilon, these epsilons are small numbers, but they are, they have an order like that. So different groups, and then they have gaps. Then what we can show is, so even if you have, if you're dealing with regular regression or logistic regression, then your loss function the gradient of your loss function has this kind of multi-scale structure. And for deep neural network, it's the same. It's same is an overstatement, because what we can do is we say that the gradient of the loss function with respect to the weights in the input matrix to the matrix, connecting the input layer to the first hidden layer, has this multi-scale structure. We can look at the distribution again of the singular value, and it shows some kind of persistent properties, that how they decay in different stages of the training. Furthermore, we can have if you assume that all the gaps are the same, and then your coordinates are in powers of epsilon, then you can have this general multi-scale expansion of the loss gradient. For all layers, you can have this multi-scale expansion. Okay, the next thing we can say at the moment is that because what matters is really the eigenvalue of the Hessian function of the loss, because that would determine how big your learning rate should be when you do stochastic gradient descent based algorithm. So we can have an estimate on the eigenvalues of the loss of the losses Hessian with respect to the again to the input layer matrix. In practice, they also decays like that. This is a distribution of the eigenvalues, and you see that there are really gaps of those eigenvalues. So how do you I'll use 1 minute to talk about this. So if you if you look at this kind of distribution, then you can wonder, maybe you can modify simple gradient descent because you know how these eigenvalues are grouped to achieve a faster convergence rate. So this is what we do. So I will jump to here. So what we propose is what we call a multi-rate gradient descent. You start out with something very small, so with a very small learning rate, and then with a sufficient number of steps, then you adjust to a larger learning rate for sufficient number of steps, and then you adjust to even larger one depending on how many eigengroups of your hashness, and then you repeat. So this is you can say that this is a cyclic training schedule, but in each cycle you actually involve learning rate of different sizes, like that. Okay, but then the question is how small in each regime, and how many steps do you need to do? And that requires some analysis that we did. So I will go through the yeah, well, due to the time, I won't go to any of these details, but it is possible to estimate, to find out how many steps that you need to run for each group of learning rates based on your understanding of how essentially the gap of each eigengroups, and then also within each eigengroup, how the eigenvalue decays, like that. So that's possible to do. And resulting thing would be summarized in this picture over here. No, in this table over here. In terms of complexity, how many steps does one need for, in this case, gradient descent in order to converge to an epsilon neighborhood of the optimizer? The information that's in, and then the information needed is you need to select your learning rate so that the gradient descent is stable. So you need the largest eigenvalues. This is a momentum method. GD plus refers to momentum methods. And you see that there's a square root over here. And then this is our multi-rate gradient descent, Mr. GD. And then this is what you have. Instead of a 1 over R, you have log of R. Recall that R is referring to the gap here. Okay, R is, or 1 over R is the gap. And if you are able to use an optimal multi-grid, then the theoretical optimal thing is this. But you need a lot more information. You need the precise information about the eigenvalues to do that. Here, we're kind of in between. We assume that we know the gap, and then the decay rate within each eigengroups. So we call it eigenvalue clusters. Then we can have that. We can achieve faster convergence rate. And this is just 2 experiments showing the history of errors for gradient descent, and then this Mr. GD, solving this problem, a convex problem. Okay, and then we can generalize this to when L is a more general convex function, and have some kind of estimates like that. I'm gonna skip because I'm running out of time. We apply this thing to classify. This is very preliminary simulations to study how that could accelerate classification of different data sets that people commonly use. And it seems it does accelerate and provide some kind of advantages, but I'm not willing to conclude because there are many other things that may influence the success of a classifier anyway. So this is a summary. This is for the second half of my talk. Multiscale data will lead to multiscale loss function, even though your loss function has no scale, right? The way you plug in this function will induce some kind of multiscale property of your empirical loss function. And then, I think in 30 seconds, I tell you the idea of a training strategy involving cyclically using different learning rates with suitable number of steps for each learning rates. And we can prove for at least for a class of smooth convex functions, it can provide acceleration. Well, the two questions we're still trying to find out, right? How practical are these, right? Because after all, we need to be able to, for it to be practical, a prerequisite is that one needs to be able to quickly obtain some estimates about the eigenclusters, right? Without that, then this is just a bit of a fantasy, right? And then the last bullet point would be more interesting because what happens if you do this Mr. GD algorithm on a non-convex potential to minimize a non-convex potential? And at some point, your large step will let you hop to a different basin. And would you be able to say that there's a higher probability that you would linger more on the flatter region than than other places? That's for people to find out. We're working on this, but slowly on our own pace. So with that, I finished my talk.